Okay, can you see the slides?
Yes, yes.
Okay. So I would like to speak a little bit about a new area, which is somehow related to modified Bessel functions. And I was working in the last half year on this topic, and it is about so-called Kaiser-Bessel window function, which is very useful in signal processing, and it is somehow related to the special functions which I was studying in the last, let's say, 15 years. This is the abstract of my talk. This talk is based on a paper with Tibor Pogány. He is my colleague at the Obuda University. The title of the paper is the same as the title of this talk, and the paper is submitted to constructive approximation. What we are doing here is that we are going to define a new distribution by using a generalized Kaiser-Bessel window function, which is very frequent in tomographic image reconstruction. I will be not able to present all the paper. I will choose only some significant parts of the paper, and the rest I will try to just mention a few things. What is important here is that this distribution is related to the modified Bessel function of the first kind, and we made a very detailed analysis on this distribution, and we find out that actually it is an extension of the so-called Wigner semicircle distribution, which is very important in random matrix theory. It is also an extension of the parabolic and n-sphere distributions, ultraspherical, hyperspherical, or power semicircle distributions. You will see that as a limiting case, we will get back these well-known distributions. I will show you the moments, absolute moments, characteristic functions, moment generating functions for this new distribution, the cumulative distribution function. We also made some very fine analysis on the properties of the density function. I mean properties like monotonicity, convexity, and this kind of things. In some situations, we had very long and very technical proofs, and we used different things from classical analysis, methods of differential equations, Riccati differential equations, integral transforms, and I will present also some algorithms how to generate some independent continuous random variables by using some fine properties of the density function. Okay, this is the outline of the talk. First, I will speak about the introduction and some motivation of this work. Then I will introduce the distribution. I will show one way how to deduce the cumulative distribution function. What can we say about the moments, absolute moments, Mellin transforms? Also, how about the limiting and particular cases? How these Wigner distributions came into the picture? Some bounds for the effective variance, and also I will show you the sign of the excess kurtosis. It will turn out that actually we are speaking about the sub-Gaussian distribution, which is not infinitely divisible. Some kind of parameter estimation by using method of moments, but somehow tricky, mixed with recurrence relations, some generating independent random variables, the characteristic function, how is it I will show you also that the moments will determine exactly the distribution. So we have a moment determinacy problem here, and if I will have time, I will show you the differential entropy and the Rényi entropy for this distribution. And at the end, I will show you some graphs of the density function. Okay, what is the motivation of our work? In signal processing, usually the people are analyzing some signals such as sounds, images, and these are very essential in MRIs, CT scans, and also X-rays. And in this area, window function, which is sometimes called also a tapering function or apodization function, is often used to restrict an arbitrary function or signal in some way. So the main idea is that we have a function with a support. So a window function is usually zero valued outside of some interval. That interval is it is like for the density function is a support. And usually this window function is symmetric around the middle of the interval, usually near to a maximum in the middle. So we have a unimodal window function usually, and it is tapering away from the middle. So if we have another function or some wave and we would like to multiply this window function, usually the product is zero valued outside the interval. All that is left is part where they overlap. And this is why we call a view through the window. So this is why we use this name window function. And what is important here is that not the segmentation, the tapering is the main purpose of the window function. And in applications, these functions are positive functions and they are bell-shaped curves. So they look very similar like a bell curve. This kind of function are very often used in spectral analysis, design of finite impulse response filters, and antenna design. The most popular window functions are the Parsen, Welch, sine, cosine, power of sine, Hahn, Hemming, Blackman, Nuttall, and others. And there is one which is called the Kaiser window, and it is about this. It is this window function. It was used first by an electrical engineer. His name is James Frederick Kaiser. He was working at that time at Bell Laboratories. And it is about this function. Here, this I0 is the modified Bessel function of the first kind of zero order. This A is the window duration, and the parameter alpha is a shape parameter, controls the taper of the window and controls the trade-off between the width of the main lobe and the amplitude of the side lobes of the Fourier transform of the window. In image processing, usually the people are using some spherically symmetric basis functions. And these kind of functions are called blobs. And a typical specific blob used in tomographic image reconstruction is based on this generalized Kaiser-Bessel window function. You can see that now we have IM. This is the modified Bessel function of the first kind of order M, greater than -1. This M is not necessarily integer, can be a real number. Please excuse me, I want to close my window. sorry. So this WA alpha MR is a generalized Kaiser-Bessel window, but you can see that actually here R is between 0 and A, and when we have 0, we have that R is greater than A. So if I go back a little and I would like to see this one as a special case of the other one, then we have a difficulty here, because you can see that here R is between minus A and A. So we will define later a modified version of this generalized Kaiser-Bessel window. I mean, in the sense that I will use the symmetric form of this one when I write instead of 0 minus A here. Here alpha is again a parameter, a shape parameter. This parameter is controlling the blob shape. A is the radius of the blob, and R is the radial distance from the blob center. These shape parameters can be controlled, and they are completely localized in space and nearly band limited. And moreover, the projection has a particularly convenient analytical form which can be easily evaluated. This is why this kind of functions are very important in image reconstruction. Moreover, this function is isotropic. This means that its projections do not depend on the direction. So the computation of this imaging operator will be significantly faster than in other cases. And there is an interesting study about these basis functions, and some researchers find out that optimum parameters in some sense are m is equal to 2, a is equal to 2, and alpha is 10.417. This number 2 is because in this case the blob has a continuous first derivative at the radial boundary, and this guy, this alpha, is actually the second positive 0 of the Bessel function g 7 over 2. And these optimum parameters were also found by using the Fourier transform of the window function, by using another analysis. And what we would like to do here is to consider the symmetric form, to define a distribution, and to look at from the mathematical point of view, from a classical analysis point of view, and also classical probability theory point of view, the properties of this distribution. So this is the symmetric generalized Kaiser-Bessel window function. You can see that here we have a nu instead of m, and here we have a symmetric interval from minus a to a. If we make a picture of this function, we can see that it is a bell-shaped curve. It is very nice. It is unimodal. In some part is a convex function. Near to the maximum point is a concave function. Moreover, it is a log concave, geometrically concave function, and so on. But the area between the graph of the function and the real axis is not 1, so we are going to normalize it. So if we look at the integral of this function from minus a to a, it is not hard to prove that actually we get this number. Here, this I nu plus 1/2 and I nu are the modified Bessel functions of the first kind. So we have a quotient of these functions. So if we put this number in the front on the power -1, then we get that this is a density function. This is a probability density function. So this phi A alpha nu will be called from now as the Kaiser-Bessel distribution with the parameter space A alpha and nu. A and alpha are positive numbers, and nu is a real number greater than -1. In the theory of distributions, there is a Bessel distribution, which is called the Mackay distribution of the first type, which has the probability density function like this. And if we make a transformation, so instead of x here, we write alpha square root 1 minus x square over a square, and we change beta b here to be 1. Then we obtain this transformation of the density function of Mackay, and we can see that what we have here, so this Kaiser-Bessel probability density function is actually completely different. It's not the same because of this this exponential factor, and this c is greater than 1, so we cannot put here 0. When c is less than 1, then we have another type of Mackay distribution, but that one involves km instead of im. So it involves the modified Bessel function of the second kind. Okay, if we would like to see the cumulative distribution function for this Kaiser-Bessel distribution, then of course we need to compute this probability. And because of the symmetry, of course, we can write the cumulative distribution function as 1/2 plus this guy, which is the integral from 0 to x. Because the integral from -infinity to 0 is 1/2 because of the symmetry. So actually we need to handle this, this integral. The problem here is that here we have x, so it is a little bit more complicated. In our paper, we have 3 ways how to handle this problem. Now I will show you only one, the easiest one. So the idea is to make a transformation. So here, instead of instead of this guy, we will write u, and we have this transformation where this g(ax) is this square root 1 minus x squared over a square. So we need to handle this integral, and what we do is to expand this integrand into the Taylor series, into the Maclaurin series, and we change the order of the summation and integration via the Tonelli theorem. So if we interchange here the sum and the integral, we obtain this kind of expression for this this integral, and this one omega n a alpha nu x is a difference between some hypergeometric functions 1f2, and here this ga is the same notation for the square root 1 minus x squared over a square. So if we collect these relations, we obtain that the cumulative distribution function looks like this. So this is one of the representations. Okay, what can we say about the moments of the Kaiser-Bessel distribution? So because of the symmetry, of course, we obtain that the expected value is 0. If we go further and we are looking for the expected value of x squared, then we need to compute this integral, and we obtain this quantity after a change of variable and also some tricks over here. Moreover, if we go further and we have x power 4, then we can see that what is changing here? Here we have +1. Here we have also in the power +1 comparative to this expression. Here we have 4 instead of 2, and here we have a number 3. So if we look at more generally, so we look at the expected value of even orders, because the odd order moments vanish because of the symmetry. So we have this kind of integral, and this is the final result for the even or order moments. By using the recurrence relations for the modified Bessel function of the first kind, I mean the three-term recurrence relation, then we can obtain a recurrence relation for the moments, which can be written in this way. So we have this kind of recurrence relation for the moments. Moreover, if we go further, we look at the Mellin transform of the absolute value of the variable x, then we arrive to this this expression. And if we look at the absolute moments, then we have this quantity. And by using the fact that this this guy here in with respect to nu is a decreasing function, this is a result of Lorch, who proved that this I nu plus beta alpha over I nu alpha is decreasing as a function of nu for every alpha and beta positive numbers, such that we have these conditions. So if you apply this result, then we immediately get that actually we have somehow an ordering relation between the absolute moments. So if x nu is follows this distribution and x nu this one, then if mu is greater than nu, then the absolute moments are reversed. So we have this kind of ordering relation for the absolute moments. Moreover, we can see that actually we have this kind of inequalities, that this function as a function of R is a non-decreasing function. This is a Lyapunov type inequality. This follows from the Hölder-Rogers inequality for integrals. Moreover, if we consider the Gauss-Winkler inequality for the moments, for the absolute moments, so this one, we can see that actually this quotient is greater than this expression. And if R is greater than S, then this guy is greater than 1. So this is a better bound for that quotient of the absolute moments. We also know that if we look at the absolute moment of random variable, that is logarithmically convex, that means that its logarithm is convex. So we have this kind of inequality, which we call in the theory of orthogonal polynomials and special functions as a Turan type inequality. This is a classical thing. In this case, actually, by using the Cauchy-Bunyakovsky-Schwarz inequality, we can extend a little bit, and we can have this kind of more general inequality. And if we rewrite everything in terms of modified Bessel functions, then we obtain this kind of Turan type inequality for the modified Bessel functions. This result is not new. It was proved recently by two different groups in two different papers by using two completely different methods. It seems to us that actually this is the simplest proof for this kind of inequality, because it follows immediately from the representation of the absolute moments. Okay, what about the limiting in particular cases? If we look at the asymptotic behavior of I nu when x is I, and this delta 1, delta 2, and so on can be written in this way. We have a, you can see that we have a convolution type recurrence relation here, and we are using these quantities, which are often used in the asymptotic analysis of Bessel and modified Bessel functions. Okay, if we write nu equal to 1/2 and 1, and also a equal to 1 and nu equal to n-1/2, then we obtain these particular cases. This guy is the Wigner semicircle distribution function. This one is the parabolic distribution function, and this one is the Wigner n-sphere distribution. The semicircle distribution appear also in number theory. It is called as the Sato-Tate distribution. Moreover, if we consider this function, now instead of a we have 2, then we obtain this density function, and this is called the ultraspherical or hyperspherical distribution. And this distribution contains all Gaussian distribution with respect to the 5 fundamental independence in non-commutative probability. The Wigner semicircle distribution is very often used in random matrix theory, and it was discovered by Eugen Wigner, who was a physicist, and he used this distribution for large random matrices. Moreover, if we look at the asymptotic form of the density function, when instead of nu we write nu plus 1/2 and alpha tends to 0, then what we get here is actually so-called person type 2 distribution, which is also very often used in probability theory and statistics. And this is also called as the power semicircle distribution in probability theory. If nu tends to infinity, then we obtain this asymptotic relation for the density function. And if we apply all these things to the moments and absolute moments, then we obtain that if alpha tends to 0, we have this asymptotic relation for the moment. Some particular cases, the simplest cases are when we have instead of nu 1/2 and -1/2, then we arrive to the hyperbolic sine and hyperbolic cosine functions. We have these density functions, and in the case of -1/2, in this case, we have this symmetric Kaiser-Bessel window function, and this is called the hyperbolic cosine window function, which appears also in electrical engineering literature. So you can see that actually there is a close connection between these two functions. Okay. In statistics, there is a notion which is called effective radius and variance of probability distribution. This is defined via the second, third, and fourth order moments. In our case, because the odd order moments are 0, we will actually use the notion of effective radius and variance for the absolute moments. So if we use the second, third, and fourth order absolute moments, then this will be the effective radius and this will be the effective variance. We can see very quickly, because of this this inequality. This is a general Turan type inequality by Lorch, Lee Lorch. We can see very quickly that actually this quantity is less than 0 So if we look at the effective variance, then we obtain that this will be always less than this 0.17, and it is also greater than 0. So we have a very sharp bound for this effective variance, and also by using the fact that this quotient as a function of x is an increasing function, and we have these two-line type inequalities, the left-hand side is actually the same. We can make a transformation, is the same as this inequality. We just need to make some change of variables, and we can arrive to the equivalence of these inequalities. So if you look at these two-line type inequalities, then very easily we can obtain that actually this effective variance is between this guy and is greater than this one, which is greater than 0. Moreover, if we use a general result of Sergei Kalmykov and Dmitry Karp about some two-line type inequalities for hypergeometric functions, then we can have a better upper bound, which is this guy, where this R nu is a quotient of gamma functions minus 1. This is also a two-line expression here, and we can see that actually we can bound very tightly the effective variance. Moreover, if we use some very elementary inequalities like the Jordan inequalities for sine and cosine, and we look at the integral representation of the expression of the Turanian expression. Sorry, so I'm talking about this expression here. Then we can prove that actually the general Turan expression is greater than this quantity, where this overline omega is a quantity by using 1f2 hypergeometric functions, and we can obtain another upper bound which is better than this guy, and range of validity is also better than before. Okay, so if we look at all these things together and we use for the excess kurtosis, then this guy, this kappa, will be this Turanian expression over this quantity, and we can see that this is a negative number for all a greater than 0, alpha greater than 0, nu greater than -2. So this means that the Kaiser-Bessel distribution has negative excess kurtosis, and it is a platykurtic or sub-Gaussian distribution. Moreover, because it has a compact support, it is not infinitely divisible in the classical sense. This can be also obtained very quickly from the fact that its excess kurtosis is strictly negative. So in other words, if the Kaiser-Bessel distribution would be infinitely divisible in the classical sense, then its excess kurtosis will be non-negative, according to a result from this paper. It will be an interesting and challenging problem to see what can we say about the infinitely divisibility in the free sense, in the sense of the free probability. This problem was generated by the fact that the power semicircle distribution is freely infinitely divisible. Okay, if we would like to have some parameter estimation for this distribution, the classical way is to use the method of moments. So if we look at, for example, these three consecutive moments, absolute moments, then it will be necessary to compute to solve this system numerically, and because of these general expressions, it is not a very easy thing. Another way would be to have a free equation. So to run expression like this, and to use this this free expression and to solve the equations. Also, it would be interesting to use the fact that every quotient of the powers of two power series is also a power series, and if you look at the Cauchy product, we can identify the coefficients, and then to use the Lagrange inversion theorem, and to have a estimation for the parameters. Our idea is to use a more simple way, and we are thinking about this reconciliation, which we can obtain very quickly by using the reconciliation for the modified Bessel functions, and then by using the reconciliation in particular cases to have a system and to transform that system into a non-homogeneous linear system by using this change of variables, and then to solve this system. Here we can see that actually we have 1, 2, 3, 4, and 5 absolute moments. We have 3 equations, we have 3 unknowns, and although we have 5 absolute moments, there is no inconsistency in the system, because the moments are in connection to each other according to the reconciliation. So if we would like to have a parameter estimation by using the method of moments, then we suggest to combine the classical method by these reconciliations. So if we have these independent and identically distributed Kaiser-Bessel random variables, and we have these theoretical absolute moments, then if we estimate by the empirical absolute sample moments, we arrive to this system, and then we arrive to this estimation for the parameters, of course, provided that the denominator in the fractions doesn't vanish. And here is an algorithm how to generate independent random variables. This is based on the classical rejection method. We are using here the unimodality of the Kaiser-Bessel distribution, and we use this basic inequality that in x equal to 0 we have a maximum of the density function, and we use the classical rejection method to create independent random variables. So we are looking for the uniform distribution on the interval 0, 1, and also for the uniform distribution on the interval -AA, and we repeat the procedure until we get this, and this is related to this inequality. We have a better algorithm, and this is also based on the classical rejection method, but we use a more fine inequality, and this is this one. So this phi a alpha x nu x is actually less than this guy times normalizing constant here, and what is important here is that instead of alpha we put here 0. Why is this important? Because when we have here alpha equal to 0 is actually limiting case, and that limiting case is well known in the literature, and it is very easy to generate random variables which follow this distribution. So this is the main idea. The proof of this inequality is actually based on the fact that the Bessel function of the first kind is an entire function. It has infinitely many zeros, real zeros. So according to Weierstrass, it has an infinite product representation. And if we look at the Bessel function of the purely imaginary argument, that is the modified Bessel function of first kind, then we arrive to this infinite product representation where this g nu n is the end positive zero of the classical Bessel function of the first kind. Okay, here is the second algorithm how to create independent random variables of Kaiser-Bessel distribution. The main idea is that before in the algorithm 1, we were looking for the area between the bell-shaped curve and horizontal line which is crossing the point, the maximum point of the density function. And now in this algorithm, actually we are looking for the area between the bell-shaped curve and another bell-shaped curve which is greater than this one on the wall support. Here is a diagram. The red diagram has been generated in Matlab for these parameters: a equal to 2, mu equal to 2, and alpha equal to 10.417. We were using this kind of computer for this, and in the blue diagram we had these parameters, and the sample was 10 power 6, and we had a runtime 3.35 seconds for this blue one, and we had 5.15 seconds for this red one. So this was generated by using algorithm 1. This was generated by using algorithm 2. Okay, what about the characteristic function? If we look at the characteristic function of the distribution, then after some tricky change of variables and Sonin integral representations, we arrive to this expression. This is a quotient between the Bessel function of the first kind. However, you can see that this term here can be negative. That means that in the case when it is negative, we have a modified Bessel function of the first kind. So this is the characteristic function of the Kaiser-Bessel distribution. This is the Sonin integral formula which we are using here. From the characteristic function, we can obtain immediately the moment generating function. So this is the moment generating function. This is a positive log convex function. We can apply the whole machinery of classical probability theory. For example, if we use the Hoeffding inequality, then we obtain that the moment generating function is always less than this exponential term. Moreover, if we use this inequality from the theory of special functions, we obtain this bound, and we can have other bounds also. Moreover, if we look at this Lombel expansion in terms of Neumann series of Bessel functions, and we make this change of variable so that instead of the Bessel function, we have modified Bessel function, and then we go back here, we can see that actually we can obtain also the moments of the the characteristic function of the Kaiser-Bessel distribution by using this identity. So this is a second way how to obtain this kind of things. What about the moment determinacy problem? The question is that if is x the only random variable was set of moments or mu n. In our case, we face with a so-called hamburger moment problem, and because of this upper bounds for the moment generating function, there is a condition of Kramer which says that if there exists a constancy for which the moment generating function satisfies this inequality for all t in this way, then all moments are finite and X is moment determinate. And this is our case. In our case, these inequalities fulfill the Cramer condition, and the Kaiser-Bessel random variable is determinate via the well-defined moment sequence. This is the differential entropy. This is the so-called Shannon entropy of the distribution. We have this integral, we have a logarithm here. So if we make this change of variable here, then we need to evaluate this kind of integrals. And after a long process, and by using many different things, for example, a result of Ismail and May on the quotient of modified Bessel functions, we arrive to this complicated expression of the Shannon entropy. This guy here, F210,201, is the Campe-de hypergeometric function. This is a hypergeometric function of two variables, and the rest is the same. 1f2 is hypergeometric function, and this is the m positive 0 of the Bessel function of the first kind. Finally, if we look at the Rényi entropy for the continuous random variables, then we need to face with this integral. We have here a power lambda, and also here an extra power lambda here. And after some clever computations, we arrive to this expression for the Rényi entropy. And as a byproduct, we obtain this relation by obtaining in two different ways the Rényi entropy. This gamma k lambda is this expression in terms of k, m, and lambda. Okay, here are some pictures. This is the density function for different values of alpha. You can see that these are nice bell-shaped curves. There is a behavior with respect to alpha, a, and mu. So in our paper, actually, we were able to describe almost completely the monotonicity with respect to a, alpha, and mu, and also the log convexity and log concavity with respect to x, to find out the inflection points. And here is a picture about the logarithmic concavity. You can see that we have log concave functions. This is for different values of alpha. Here is another picture when mu is changing. So a, alpha, and are fixed, and for different mu's, this is the picture for the density function. It is very interesting that actually we were able to show that this density function satisfies a partial differential equation. Another thing is that the monotonicity with respect to a and with respect to a is related to Riccati differential equations, and with respect to alpha and mu, these two monotonicities are related to each other. And here is a picture about the monotonicity with respect to mu. We can see that we have strong decreasing behavior from a number, and the challenging problem for us is to find for which nu we have a maximum here. It is not easy in the sense that we need to face complicated Cauchy products in which not only the orders are different, but also the arguments. So the classical theory of Watson from the treatise on the theory of Bessel functions doesn't work here. So we need to discover some new things to handle these problems. Up to now, we we have a value here, and that value is around 0.9, and we were able to prove that for every nu greater than 0.9, these density functions are decreasing with respect to the order. Here are the references. This is the paper of Kaiser, in which he defined first the window function. This is from 1974. This is a paper of Levitt from 1990. He was using the Kaiser-Bessel window function in digital image representations, and he computed a lot of things for this window function, and we extended his results actually. This is another paper of Levitt where he used these results. This was published in Physical Medical Biology. And here are some papers which also were very useful in our study. This is a paper of Mattei and Levitt, also related to signal processing and image reconstruction, and another one by Powdell. And finally, here is a paper of Prabhu. He is a professor in IIT Madras, and he wrote a book 8 years ago about window functions, and I found this book very useful. Thank you very much for your attention.
Thank you very much, Professor Baricz, for such an informative and interesting talk. If anybody wish to ask any question regarding this lecture, they may ask. I think no questions, so thank you so much. Thank you very much, Professor Baricz.
Professor Baricz, thank you very much for your enlightened lecture.
Welcome.
Actually, I have a few questions.
Okay.
If you permit.
Okay.
Since I think this density function I think you have developed this density function. I just wanted to add whether you have considered analysis for this.
Please ask again.
Have you considered the Bayesian analysis for this density function?
No.
I think you can consider that. Also you can be added. This paper can be more good if you can add the Bayesian consideration also. And also, I think that since you have considered two entropies like Rennie's entropy and Shannon entropy, you can also consider that Harvard-Charvard entropy is there. Then Sally's entropy is there. Another important areas where you can work. And Professor Mattei has also introduced one entropy called Mattei's entropy is there. So I think these areas this function can be extended to that areas also. In this in your slides, I just wanted to ask equation 2. Can you take that page maybe in the second page, right?
Okay.
Yeah. Not here. Yeah. This one. Equation 2. Yes. Here, this in this density function, this modulus of x is less than or equal to a means can it be less values? Can you take negative values also for this? Is it like that or? It is from minus a to a. So since it is a density function, it should be positive. As I know whether this function remains all the time positive.
Please ask again.
I just wanted to ask whether whenever a is negative, also function is positive or not, because this is a probability density function. So that is what I am asking.
Yeah, a is a positive number.
Yeah, but here it is minus a to a. You have written A is a positive number means minus A to A is, then A can be negative also means. So
but because of the power 2 here, everything in the square root is positive, and this guy is of course a power series with positive coefficients. So indeed, what we have, that is a function in the upper semiplane.
And what about this A in the denominator here? That in the first part, that is A I nu plus half. Yeah, that one. It's a function, right? I think it is a function, right? It's a function.
So this is a value of I nu plus 1/2 in alpha. Alpha is a positive number. A is a positive number.
Okay, it's a notation. I think then it is a notation. Is it a notation like A I nu plus half? Is it defined here in this paper or?
So let me tell you again. So A is a positive number.
Yeah.
Alpha is a positive number.
Okay. I understood.
Okay.
I understood. Okay. I was not aware of this. So maybe
and you can be negative number because that is in the order, and that will not disturb the problem because it is here and also in the order. But that can be negative. That is not a problem. But A cannot be negative because otherwise we have a problem here.
Yeah. That is what I am asking.
Yeah. Of course.
A cannot be negative, right?
No.
Yeah.
No. But because of the motivation cannot be, and also because of the motivation cannot be negative, because A in this field is a window duration, and if we look at the basis functions, then A is the radius of the blow. That should be a positive number. So in practical situations, it cannot be negative. Also from our point of view, cannot be negative.
Yes.
Doesn't make sense.
Yes. And can you take equation page number 11? In equation 11, page 11.
Okay.
Yeah, previous page. Yeah. Here, what is this 1 omega? It is a trichotomy function. Is it a trichotomy function? That is it that this omega?
This is just no. This is just a notation. So instead of this difference, I wrote this guy. That's all.
Okay. Okay.
Just a notation. It's nothing related to other special functions.
Okay. That's all. Thank you very much, Professor Baricz, for your nice talk. And in fact, I have worked on some of your works on generalized Bessel function. I have done some work. I hope you have seen that paper also.
Yeah, I have seen your paper.
Yeah. Okay. Thank you.
You're